So in this video, we're going to look at sequences, and we're going to look at specifically at the formulas. So first, we're going to look at formulas that are both explicit and recursive, and how we can use those formulas to find the values in the sequence. And then we're going to do the opposite. So we're going to have a sequence of values, and we're going to try to identify the formula, try to select a formula, either recursive or explicit, that we can then use to prove other things about the sequence. So let's start with our first example, is an example of an explicit sequence. An explicit sequence has a formula that is in terms of n, so that you can jump to any term in the sequence without going through all of the previous terms in the sequence. So you have an, and then again, your formula depends only on maybe some constants and values of n. So typically sequences are going to start counting at either 1 or 0. If you have an undefined term when n is 0, then of course you skip over that. So in this case, since n is in the denominator, we're going to start counting at 1. Sometimes sequences will be expressed so that they tell you when they start, but typically algebraic sequences will start at 1, and geometric sequences will tend to start at 0. Okay, so the first term in the sequence, that means we're going to replace n with 1. So we have 5 minus 1 over 1 squared. 5 minus 1 is 4. So that's the first term in our sequence. A2, now we're going to replace n with 2. So 5 minus a quarter. And that, if you simplify that, you get 19 over 4. And then the next term in the sequence, A3, we replace n with 3. 5 minus a ninth is going to simplify to 44 over 9, and so on. N is 4, we get 5 minus a 16th, and then when n is 5, we get 5 minus 1 over 25. And what you can see is that each of these fractions in our formula is getting smaller and smaller, and so we can actually use this formula to prove that the limit of this sequence is 5. Now let's look at our second example. This is a recursive formula. Now, in a recursive formula, you have to specify one or more seed values depending on how many terms the recursion requires. So in this case, it's requiring only one previous term in the sequence. So an is the last term in the sequence that you calculated, and then an plus 1 is the next one in the sequence. And here our seed value is a1 because we have to have a place to begin. And so the first value is 9. So A1 is 9, that's given to us. Then the second one we calculate by replacing AN with the previous value we found. So 9 squared divided by 3, 9 squared is 81, divided by 3 is 27. Then 27 is now what goes into our formula for AN in order to get a 3. 27 squared divided by 3, we end up with 243. And then we continue in this procedure. 243 goes into this, it gets squared, divided by 3. You have a very large number. I left out the comma, even though it's very hard to read because commas with separating terms by commas doesn't make it easier to read. And you would continue in this vein, getting much larger and larger and larger numbers because you are multiplying, you're squaring these numbers that are growing very quickly, very fast. Another way that you can write this sequence is that this is 3 squared, since these are all powers of 3 to start with. And this is 3 cubed. And then this is 3 to the 5th. And this is 3 to the 9th. And this is 3 to the 17th. And it turns out that we can redefine this. We may be able to find another formula for this sequence by writing it in terms of its powers of 3. So that there may be use in writing it out sort of as numbers, but there may also be advantages in finding other ways to express the series. One thing I'm noticing as I'm looking at this is that these are all like this is 1 plus 1, and this is 2 plus 2, and this is sorry, this is 1 plus 1, and this is 2 plus 1, and this is 4 plus 1, and this is 8 plus 1, and this is 16 plus 1. These powers are all powers of 2 plus 1. So there may be a way of writing this formula explicitly so that you can have a formula where you can jump ahead. Maybe I want the 5th term in the sequence, and I don't want to calculate all these other terms. If I can find a formula, an explicit formula, I may be able to do that. Now, in some textbooks, they will base the formula on AN, and then you will solve for AN plus 1. But if you count your last term in the sequence as AN, you may also see other textbooks use the previous term in the sequence as AN minus 1 and AN as the term that you are solving for. These formulas are exactly the same. They're just notated a little differently, whether we call the last one we calculated as AN or whether we call the next one we're calculating as AN. All right, now we want to talk a little bit about finding formulas for sequences. And this can be quite hard because we have to establish a pattern and then derive a formula for it. And so we want to look at some common types of sequences and think about them in terms of the patterns that they form, and then use those patterns to come up with our formulas. Now, this is going to be a very important thing to come up with for a couple of different reasons. First of all, if you want to find the limit, it's much easier if you have an explicit formula in order to find the limit rather than a recursive formula. Recursive formulas are not always entirely clear, and they may depend on the seed value as to whether they're going to converge or diverge. Whereas if you have an explicit formula, that information is already included in the formula for that particular first value. And then you have a better chance of actually just using it like a function and figuring out where it goes. Also, when we're doing Taylor series later on in Calculus 2, we're often going to be deriving these strings of polynomials with a bunch of different coefficients, and they are much easier to work with if we can come up with a nice compact formula for the coefficients in the Taylor series, so that we can write them as a summation instead of having to deal with them as a string of terms that don't really have an underlying pattern. All right, so some things to think about when we create a formula for our sequence. Now, a lot of these are going to be, the idea is going to come up with an explicit formula. And so it's something to think about. If you can come up with the recursive formula, that may give you a start. But then if you could come up with an explicit formula, that's usually, as I said, easier to work with. So the simplest kinds of formulas are going to be sequences, are going to be arithmetic sequences, where you are just adding a constant value every time. So for instance, odd numbers, 3, 5, 7, 9, these all differ by 2. So the way that you test to see if you have an arithmetic formula is you take consecutive terms and you subtract them from each other. The larger one minus the smaller one, or the one further down the line minus the one earlier down the line. And you will, if you get the same value every time, that is an arithmetic sequence. So in this case, if I start counting at n equals 0, I can write this formula as 2n plus 3. If I started counting at n equals 1, I would have to write this as 2n plus 1. The 2 is telling me the step size in this case. And you can see by plugging in different values of n that you can generate the sequence depending on whether you start at 0 or 1. In this case, again, n equals 0. In a geometric sequence, the terms are going to differ by a constant multiple. So you want to find the ratio of consecutive values and see if they turn out to be the same. So in this case, I'm doubling each time. So my common ratio is this 2. And my first value in the sequence is going to be 3. So if, again, starting with n equals 0, 2 to the 0 is 1, and so I get 3. But when 2 to the 1 is used, I get 2 times 3, which is 6. When this is 2 to the 2, I get 4 times 3, which is 12, and so forth. Now, factorials are another thing that will tend to show up, particularly in our Taylor polynomials, and you may never have encountered them before, but basically the idea of a factorial is that you're going to start with an integer and then you're going to multiply by every number less than that until you get to 1. So 7 factorial, for instance, is 7 times 6 times 5 times 4 times 3 times 2 times 1. And so 1 factorial is 1, and 2 factorial is 2 times 1, which is 2, and 3 factorial is 3 times 2 times 1, which is 6, and 4 factorial is 4 times 3 times 2 times 1, which is 24, and so forth. Now, 0 factorial is defined to be 1 also, and so again, this is a kind of pattern that you want to look for. If you see something like this in your formulas, you should be thinking factorials. Power series, so powers of numbers are also very common. So n squared, n cubed, things like that. And so again, that's something that you want to look for. 1 to any power is 1, but then 2 cubed, 3 cubed, 4 cubed, 5 cubed would be 1 over n cubed. Similarly, 1/4, 1/9, 1/16, 1/25, that would give you n squared, and so on. So think about powers, squared powers, cubed powers, even fourth powers. The higher powers are sort of uncommon, of course, at least in sort of practice examples, but it is worth, sort of looking for those sequences of powers that you can maybe use as a basis for finding your pattern. You also want to take account the possibility of having alternating signs. So alternating signs are usually expressed in a formula by -1 to the n or -1 to the n plus 1, depending on whether you're starting at 1 or 0 and whether your first term is positive or negative. Since I started counting at 0, then -1 to the 0 would be a positive sign. When n is 1, then I will get 5 here, and -1 to the 1 will be negative. So that alternating sign component is usually expressed in this way. Now, another thing to kind of think about is whether or not your formula follows a pattern, but nonetheless is 1 off or 2 off from that pattern. So if you have a sequence like 0, 7, 27, 63. Notice these are all 1 off of the cubes. Or maybe you will have n squareds where you would have 0, 3, 8, 15, 24. So 1 off of the squares, and they could be larger or smaller. So again, kind of keep that in mind as, okay, it's not quite one of these perfect squares, but it's a shift off of one of those. Another thing to kind of keep in mind is that you can find patterns in the numerator and the denominator separately. So if you have something very complex going on, it may be much more helpful in order to look at them as being a pattern in the numerator and a pattern in the denominator. Now, you always want to check that if you come up with a pattern for the first couple of terms in the series, that your formula still applies to the 4th and 5th terms. Often there is more than one way to come up with a pattern for 3 terms. And then it's the 4th term that's going to tell you, okay, yes, that still applies. Okay, the 5th term will narrow it down even further just to be certain that your formula works, because sometimes you can get very complex formulas that seem like they're simple, and then when you try to check the 4th or 5th terms, they will not work. And then one last thing to consider is that particularly when you have fractions, you may have terms in your sequence that have been reduced. And so if you start to see a pattern maybe on alternating terms or something like that, you may need to rewrite your fractional expressions as unreduced forms or as equivalent fractions so that you can more carefully establish that pattern. So these are some tricks to think about. And then let's do an example. So let's come up with a formula for this sequence 1, negative 2/3, 4/9, negative 8/27, etc. So the first thing that's clear is that this is a alternating sign series. The second term is negative. The fourth term is negative. So we know that we're going to have either a -1 to the n or a -1 to the n plus 1. Again, it's going to simply depend on whether we start with n equals 1 or n equals 0 and whether the first term is positive or negative. So for power series, for things like this with exponents, it's common to start with n equals 0. But if you have things in the denominator, you may have to start with n equals 1, depending on what that expression ends up being. Now, it is looking like if I look at these denominators, I'm also getting multiples of 3. So maybe this is a 1 and this is 3 to the 1. This is 3 squared. This is 3 cubed. That's going to suggest something. In my numerators, I also have 1, 2, 4, 8. These are powers of 2. So that's suggesting that I have a multiplier of potentially 2/3. Since this 1 times 2/3 would give me 2/3, and times 2/3 again would give me 4/9, and so on. So I'm starting to see there's a pattern, and now I just want to check. Am I starting with a positive number or a negative number? I'm starting with a positive number, and I don't have n's in my denominator, so I can start counting at 0. So -1 to the 0 is 1 times 2/3 to the 0 is going to be 1. And then if n is 1, this becomes -1 copy of 2/3. So this is going to work, and I can continue checking a couple more terms, and I see that it will satisfy. So I don't have an extra multiplier for the series, like my previous example where I started with a 3 times 2 to the n. Here I just have basically alternating -2/3 to the n. And so I can separate it out, or I can recombine it in a single number to the n. Now, remember, you can't do this if there is no power of n here. You can't stick things inside an exponent if they don't already have the same exponent. So we couldn't simplify our previous 3 times 2 to the n to 6 to the n, because that definitely would not work. We're not raising 3 to a power, we're only raising the 2 to a power. And here we're raising the negative and the 2/3 to the power. And so we can recombine them. And then let's look at one more example. In this case, we have some variables. Again, this is common in Taylor series when we get later on into the course a little bit. And so let's think about our powers of x that we have here. Again, you can take the numerator and the denominator apart. I've got essentially x to the 0 in the 1, x to the 1, x to the 2, x to the 3, x to the 4. So the x to the n piece is very clear. Now, what's going on with the denominators? Now, again, what I can do is I can rewrite these as fractions as 1/1 and x/1. And then the sequence that I get in the denominators is 1, 1, 2, 6, 24, which, as we noted above, is a factorial formula, starting with n equals 0. Now, since this was also x to the 0, that 1 is, then I can start my formula counting with n equals 0. And in that case, I would have x to the n over n factorial. And again, just to double check, if n is 4, then I'm going to get x to the 4th over 4 factorial, which is 4 times 3 times 2 times 1, which is in fact 24. So starting at 0, this is the correct formula. Now, you're never going to get good at this without doing a lot of practice examples. And again, sometimes it can be useful to come up with a recursive formula and then use that to come up with a explicit formula. But often you can go directly to the explicit formula unless the sequence is extremely complicated. There are examples of sequences like the Fibonacci sequence that use multiple previous terms. In the case of Fibonacci, 2 previous terms. And then that deriving a formula for that is in fact quite messy. But if you're only using one previous term, you can usually come up with an explicit formula that will allow you to do a lot more with the sequence.